Hello everyone. So here in this video we are going to learn about the second kind of substitution cipher, which is called as multiplicative ciphers. Just like in the previous cipher which we have studied, that is Caesar cipher, here also substitution has been done with a slight difference. In Caesar cipher, how we substituted is by adding a key number to the plain text number. But in case of multiplicative cipher, instead of addition, we are multiplying a key number to the plain text number to get the cipher. Okay, so in multiplicative cipher, the plain text as well as the cipher text will be integers in the range from 0 to 25 or within the range of 26. Okay, and the decryption involves multiplying with multiplicative inverse of the key. So just like in Caesar cipher, in order to decrypt, what we did is subtract the key from the cipher text number. So here instead of that, we will do a multiplicative inverse in case of a decryption. So encryption and decryption are in the inverse of each other. So let's see the equations for that. As we can see, so here there is a plain text. So this plain text is represented by P. K is the key. So instead of addition in case of Caesar cipher, in multiplication cipher it is multiplication symbol. Okay, so P into K mod 26 will give you the cipher text number. Okay, now in case of decryption it is the other way around. So in decryption you have the cipher text number multiplied with the inverse of the key, so that is represented by K inverse, and then you take a mod 26, you will get back the plain text. So this is the basic concept of multiplicative ciphers. Now let's see an example. So this is a table that shows you the different alphabets ranging from A to Z, how you can perform multiplicative ciphers on these alphabets. So A, as you already know, the number representation for A is 0. So 0 when it is multiplied with the key 7. So in this example you are using 7 as the key number. Okay, so when you are multiplying 0 with 7, you get 0 itself. So 0 mod 26 is 0. So you have the cipher text also as A, because the number corresponding to the alphabet A is 0. Now for the next alphabet B, you know that the number corresponding to the letter B is 1. So 1 into 7, where 7 is the key. So 7 mod 26. 7 mod 26 will give you a remainder of 7 itself. So which is the alphabet corresponding to the integer number 7? It is H. So likewise, all these alphabets ranging from A to Z are being represented here. Now let's take another example. So let's take like this example, M. Letter M, the representation of M is 12. So 12 into 7, when you take a mode of 26, you will get a remainder of 6, which is nothing but the alphabet G. Okay, now you have P. So P, which is 15. 15 into 7 divided by 26 will give you a remainder of 1, which is nothing but the letter B. Okay, so here 70 more 26 for letter K. K is represented by the letter 10. So 10 into 7, 70 more 26 will give you a remainder of 18, which corresponding to the letter S. So this is an explanation of how different letters in the alphabetical sequence are being multiplied with a key 7 in order to get the multiplicative ciphers. Okay, so that's about multiplicative ciphers. For better understanding, let's see another example. To encrypt a message hello with a key of 7. So here also we are using the key 7. It is not necessary that multiplicative ciphers always use key 7. You can use any keys. Okay, so the first step here is to convert or represent this particular message hello and write it in terms of the integer representation. So each and every letter is represented as integers in the alphabetical sequence. H with 7, E with 4, L with 11 and O with 14. So now we are going to apply the mathematical equation for encryption using multiplicative ciphers. This is nothing but P into K mod 26, right? So P is the plain text number into K. K is the 7 which is given in the question, mod 26. So 49 mod 26 will give you a remainder of 23, which is nothing but the plain text X, ciphertext X. Now next you have to encrypt E. E, the corresponding letter for the number for the letter E is 4. 4 into 7 is 28. 28 more 26 will give you a remainder of 2, which corresponds to the alphabet C. Now the next letter is L. The corresponding letter for L is, number for L is 11. 11 into 7 is 77. 77 mod 26 will give you a remainder of 25. We know that 78 mod 26 is fully divisible. So we assume that 25 will be the remainder when you multiply 11 by 7 to get 77, and when you take when you divide it with 26, you are left over with a remainder of 25. So 25 is nothing but the corresponding integer representation of the letter Z. Now this is represented in the next step also, because L is repeated here 2 times, and O is 14. 14 into 7 more 26 will give you 20, which corresponds to the letter U. Now we'll get the cipher text for hello as X, C, Z, Z, U. Now we need to apply the decryption. So in order to apply the decryption, first we need to find out the value of 7 inverse, or the multiplicative inverse of 7 mod 26. Okay, so the multiplicative inverse of 7 mod 26 is computed using an encryption using an algorithm called as Euclid's algorithm and extended Euclid algorithm. So this is a part of the third module, or which I will be putting up another video on how to compute extended Euclid's algorithm and how to compute inverse, multiplicative inverse using extended Euclid's algorithm. So right now I am not covering that, but for the understanding the decryption concept, we will first find out 7 inverse mod 26. By applying extended Euclid's algorithm, you will get 7 inverse as 15. Okay, so this 15 is our K inverse. We have seen that for getting back the plain text, the formula that is applied is ciphertext number multiplied by K inverse mod 26, right? This will give you back your plain text. So let's take for example the first example, which is X. Okay, so X is nothing but the ciphertext corresponding to X is 23, or the ciphertext number. So 23 multiplied by K inverse, which is 15, which we just found out, mod 26 will give you an answer of 7. Now for the next letter C. So C is the ciphertext. So ciphertext corresponding to that number is 2. 2 multiplied by K inverse, which is 15, mod 26. When you take on a calculator, you will get it as 4. And for the next alphabet Z, the integer representation of Z is 25. So 25 into 15 mod 26 will give you back a number of 11. And again you have Z, which is 25 into 15 mod 26. When you apply, you will get 11. Then you have the last one, U. The integer representation of U is 20, right? So 20 into K inverse, which is 15, and mod 26 will give you a number 14. So see here, 7, 4, 11, 11, 14. 7, 4, 11, 11, 14 corresponds to the letters H, E, L, L and O. So we have got back our plain text from the ciphertext when you applied this particular formula. Okay, so how did we find out the K inverse, that is 7 inverse mod 26? It is found out from the extended Euclid's algorithm. Okay, so extended Euclid's algorithm, I'll be putting up another video separately on how to compute inverse or multiplicative inverse using an extended Euclid's algorithm. Okay, so this is just to show that you can actually decrypt it using the K inverse concept. Okay, now moving on to the next ciphers, or the next substitution cipher, which is called as the affine cipher. Affine cipher is a combination of the additive and the multiplicative ciphers with a pair of key. We have seen that Caesar cipher used additive and multiplicative ciphers used multiplication. So affine cipher, you're going to combine both addition and multiplication into one cipher, and also using two keys. Here two keys are used, K1 and K2. It is not just one key. Okay, so let's see how the equation has been done. So first you have to find out the plain text multiplied with the first key K1 mode 26 to get a text T, and this text is added with the second key K2 and then a mode 26 is done to get the cipher text. So it is a two-step process of substitution. First you are going to multiply with the first key, the plain text number, then whatever is the result you got, you are going to add it with the second key and take a mode 26 to get the cipher. And when you do the decryption, it is the reverse thing. So the first thing is that here you're going to subtract the K2, the second key, from the cipher, and from that text you're going to apply the inverse of multiplication, mode 26, to get back the plain text. So it is the same process of Caesar cipher and multiplicative cipher, both combined together to get the affine cipher. So let's see a small example on how affine cipher is used to encrypt the same message hello with the key pair. You obviously need two keys. So 7 is the K1 and 2 is the K2. Okay. So let's see the example HELLO. You have the integer representation of those alphabets. Then the first step is to multiply the plain text into the first key K1. Then you are adding the output of this particular result with the second key, which is K2, and then you're taking a mode 26. So that is what is happening here. So here 7 into 7 is 49. 49 plus 2 is 51. 51 when taken a mode of 26 will give you back a remainder of 25, right? Only if it was 52 it was completely divisible, but we got here as 51, which means that we will get a remainder of 25 when you divide it by 26. So 25 corresponds to the letter Z. Now the next one is 4 into 7. 4 is the integer representation of the letter E. So 4 into 7, 28 plus 2, 30. 30 more 26 will give you a remainder of 4. 4 corresponds to the letter E. Now 11 into 7 is 77. 77 plus 2 is 79. So 79 when you divide by 26, so or when you are taking a mode of 26, mode 26, we know that 78 is fully divisible in 26. So 79 means you get a remainder of 1. So 1 corresponds to the alphabet B in the alphabetical sequence. So next again you have L, which is 79 mode 26, which is again 1 as the remainder, which is B. Now 14 into 7, the last letter, plus 2 mode 26 will give you a remainder of 22, which corresponds to the letter W. So hello, when it is encrypted using affine cipher, you get the cipher as ZEBBW. Okay, so this is the encryption of affine ciphers using the key pair 7 2. Okay, hope you have understood it. Thank you.